We are going to go over some of the questions from the practice test that we did not get a chance to go over in today's review game. Okay, so starting with number 7, we have Mr. Evans' standard view accelerates at 1.2 meters per second squared, and we want to find out what that is in kilometers per century squared. So we'll start with what we're given, 1.2 meters over second squared. And again, since that is a fraction for a unit, we're going to put that second squared in the denominator. So we have 2 units that we need to convert. It does not matter whether you convert meters to kilometers first or second squared to centuries first. It is up to you. I'm just going to start off with meters. So if I have meters on top, so that means I need to put meters in the denominator at my conversion factor. And I know there's 1,000 meters for every 1 kilometer. So meters on top, meters on bottom, cancel out. Okay. So now that I have kilometers in my unit, now I have to go from second squared to century squared. So if I have seconds in the bottom of my original fraction, that means I need seconds on top of my next one. And I know I have 60 seconds for every 1 minute. Okay. Be careful though, because if I have seconds squared, that's the same thing as saying seconds times seconds. So this guy only cancels out one of those seconds. So I need to do that conversion again to cancel out the second seconds. So now I have seconds on top, seconds on bottom. I'm able to cancel that out. Notice now, though, that I have 2 minutes in my denominator. So now when I do my next conversion to cancel out those minutes, that I have 60 minutes in 1 hour, I have to do that conversion twice again. Because there are 2 minute units that I need to cancel out. Okay? So now I have hours in my denominator, and I want to get rid of that so I can get to centuries. And I know that there's 24 hours in 1 day. Hours on top, hours on bottom, they cancel out. But again, I have a second hour in my denominator, so I need to do that conversion twice. So 24 hours for every 1 day. Hours on top, hours on bottom cancel out. Now we're left with days. So I know that there's 365 days in 1 year. Days on bottom, days on top cancel out. Need to do that conversion factor again though, because I have a second day in my denominator. Now I'm at years. And I know that there's 100 years for every 1 century. Oh, and it's just barely not going to fit. I have years on bottom, years on top. They cancel out. But since I have a second years in my denominator, I need to do that conversion again. Another 100 years for every 1 century. Now I have years on top, years on bottom, and they cancel. And I am left with centuries squared in my denominator, which is what I wanted. Okay, so there's a lot we had to do for this one. But now we know that we have to multiply by everything on top and divide by everything on bottom. And when we do that, we should get 1.19 times 10 to the 16th kilometers per century squared. So the main thing for this one is if you have a unit that is squared, you need to do that conversion 2 times. Okay, and then once we start doing that conversion twice, we have to do each one multiple times as well. All right. So then the next one that we did not get a chance to go over was number 9. So here we trade 3 flims for 2 flams, 8.5 shims for 4 shams, 1,000 flams for 1.2 shams, and we want to find how many centiflims we can get with our 2 kilo shams. Okay. So I just went through and highlighted all the conversion factors that are given to me in my problem. So when we're starting our math, we want to start with what we're given, which is going to be our 2 kilo shims. Notice how this guy has that metric prefix of kilo on it, so that is what we're going to need to cancel out first. And I know for every 1 kilo thing, or 1 kilo shim, I'm going to have 1,000 things, or 1,000 shims. Okay, so kilo shim on top, kilo shim on bottom, cancel out. Now I need to cancel out shims, so I look at my conversion factor. And I can see that I have 8.5 shims for every 4 shams. Since shims is on top of this fraction, I want it in the denominator of my conversion factor. Okay. So I have 4 shams for every 8.5 shims. Shims on top, shims on bottom. Oops, cancel out. Now I'm left with shams, but I don't want shams. I need to cancel that out as well. And I can see for every 1.2 shams, I have 1,000 flams. Sham on top, sham on bottom, cancel out. And then I can use my last conversion factor that for every 2 flams, I have 3 flams. Again, flam on top, flam on bottom, they're able to cancel out. Okay. However, so now we're at flams. However, we are not done because we can see that our final answer wants it to be in centiflims. And I know for every 1 flam, or for one thing, I'm going to have 100 centimeters or 100 centiflims. Okay. So now that I cancel out flims, I'm left with my centiflims, which is what I wanted to solve for. So I can multiply by everything on top, divide by everything in my denominator, and I should find that this is equal to 1.18 times 10 to the 8th centiflims. If you chose to write this as 117,647,058.8, that's A-okay. Okay, it's just some preferences to whether you want to use scientific notation or standard notation. All right, so then looking at our last one here, we have as time goes on, the height of a pile of sand in an hourglass is measured. Okay, so since it's telling us that the height is measured, that tells us the height is going to go on our y-axis. Okay, because we are seeing how our height depends on our time. So make sure that when you guys write your graph axes, you include your variable and your unit. So we can see time is going to be measured in seconds, and your height is going to be measured in centimeters. Okay. Then we'll want to plot our points from our graph. So I can see by looking at this graph that I'm going to have a direct square relationship between my time that the sand is falling and the height of the pile of sand. So if I have a direct square relationship, what I need to do to linearize is square my x values. So I'm going to manually take all my time values and square them. So I'll plug them in my calculator. Get 0 squared, and get 0. 28.7 squared, 823.69. 40.1 squared, 1608.01. 49.9 squared, 2490.01. 57.5 squared, we'll get 3,306.25. And then 64.4 squared, we'll get 4,147.36. Okay. Now that I have all my time squared values, I can go ahead and plot these on my linearized graph. Remember to make sure you show how you linearized. It's not just time anymore. It's going to be time squared measured in seconds squared. We'll have our height measured in centimeters on our y though. Once we have our axes labeled, we can go ahead and plot our linearized points. And we can see once we do that, we have a nice straight line. So we linearize correctly. Woo! All right. So then for our mathematical model, we know we use the general format, y equals mx plus b. But we are going to be more specific than that. Instead of saying y, we want to say what our y variable is, or who's on our y-axis. And that is going to be our height. And that's equal to our slope. To find our slope, we're going to pick 2 points. And again, make sure you guys use your linearized values. So I can choose the point 0, 0, and then 4,147.36, and 24.9. So I'm using my time squared values. Again, always make sure you use your linearized data. So then we find our difference of our y's divided by the difference in our x values. And we should find that the numerical value for our slope is going to be 0.006. Okay? But remember, our slope is not just a number, it is a number with units. So to find the units for that slope, we are going to do our y units divided by our x units, because that's exactly how we find our slope. We did y over x. So in this case, then, that'd be centimeters divided by seconds squared. Okay, so this whole thing right here, that is our slope. We are going to multiply that by our x variable. So if we look on our x-axis, we have time squared. So again, show how you linearize in that equation. And then for our y-intercept, we go up at our table, and it looks like our y-intercept is 0. Okay? But if we were to include a y-intercept, make sure you include units on that y-intercept as well. Okay? And that makes sense that our y-intercept would be 0, because at time 0, none of our sand has fallen yet, so our pile of sand would have a height of 0 centimeters. Then for the explanation why a graph of sand filling an hourglass might look like this, so we kind of know, if we think of an hourglass, as more sand falls, there's less blocking that hole to get down to the bottom, so sand is going to fall faster, making the pile get larger quicker and quicker. So as more sand falls, sand is going to fall faster because more sand is leaving and there is less blocking the opening. So the pile is going to grow more quickly. Okay, awesome. So if you guys have any questions on the ones that we did not get to go over in class, these ones right here, please let me know and I will be happy to help. Have a great day.